first of all, I would like to thank the organizers for inviting me to talk at the School of Future of Computing. As he mentioned, today I will be talking about quantum computing, but I will explain just the very basics of it. But then we'll have two more speakers, or two more talks on quantum. One from Alexander, sorry, the last name that I don't know how to pronounce it. Sawatsky, okay, good. Who will be talking also about quantum, mostly about quantum simulation and all different kind of computation that is based on quantum annealing, and also what the steps are, correct me if I'm wrong, to go from quantum physics to really quantum engineering to build a computer, right? And tomorrow we will have two more talks from my colleague, Professor Koen Bertels, who is the head of our section in our department, and he will be talking about the research that we are doing in Delft on how to build a quantum computer and what the challenges are, and also about a new line of research that we recently started that is quantum genome sequencing. So, say that, I would like to start my presentation. So here you see several logos. As he mentioned, I'm an assistant professor at the Quantum and Computer Engineering Department and Computer Architecture Lab in TU Delft in the Netherlands. But I'm also part of QTech. So QTech is a research institute on quantum technologies that was founded like 5 years ago, and it has a collaboration between our university, TU Delft, and TNO. TNO is an engineering company in the Netherlands. At that time, most of the people, and even now, most of the people working there are physicists, working on different quantum technologies, or how to build quantum processors. So like MB centers, Majoranas, superconducting qubits, and silicon spin qubits. And they also realized that if they wanted to build a quantum computer, it's not only about building quantum bits or qubits. So it's like, in classical, it's not only about building transistors, but also building an entire system, right? And that's why they went to our faculty, to the electrical engineering, mathematics, and computer science faculty, to see if someone there would like to be involved in this quantum initiative. And that's how Koen Bertels and other professors, Eduardo Charbon and Ryoichi Ishihara, got involved in quantum. So in QTech, we are working on quantum computation or quantum computing, but also in quantum communication and internet. There are different roadmaps. Our roadmap is the fault-tolerant roadmap that we work mostly on two technologies, superconducting qubits and silicon spin qubits. And 2.5 years ago, we started a collaboration with Intel. This is a collaboration for 10 years, and the goal is to build the first prototype of a quantum computer. So, say that, I can start with my presentation. As I said, today I will give 1.5 lectures, in which in this first presentation, I will talk about the basic unit of information in quantum that is called quantum bit or qubit. We will also talk about how to operate on those qubits or quantum gates, and also we will also build very simple quantum circuits. I would like you to do some exercises, very simple. That's why you have a piece of paper and a pen, right, or pencil, that we will do that together. And in the second part, I introduce a quantum computer simulator that we develop in TUDEP, in QTech. My colleague Nader Kamasi developed that simulator. I will explain how it works, the basics of that simulator, and then we will run the same circuits that we have done by hand, the same exercises, but using the quantum simulator. Okay, so I have 2 goals today. So the first goal is that you learn a bit about quantum. Maybe you already know, but you go one step further. And the second goal that I think it's even trickier is to keep you awake, because it's in the afternoon after lunch, and I know how difficult it is. So let's see if I succeed, okay? If I see someone falling asleep, it's fine too. Anyway, so say that. So let's just start with the basic unit of information. As you know, in classical computing, the basic unit of information is called bit, right? A classical bit is an exclusive state, meaning that it can be either 0 or 1. So you have a bit, you build data, and you transmit data by using zeros and 1. but you can only be in 0 or 1 in any point in time. In quantum computing, the basic unit of information is called quantum bit or qubit. A qubit can also be either 0 or 1, that in quantum mechanics is represented that this ket 0 or ket 1. This is called the Dirac bracket notation. So it can be in state 0 or 1, but it can only be in 0 and 1 at the same time. So this is what is called superposition. So again, superposition means that a qubit or a quantum bit can be in state 0 and 1 at the same time, okay? So that's the basic idea. Now, this combination of this superposition is expressed mathematically in this way. This is a state psi. It's expressed like alpha 0, 0 plus alpha 1, 1. Just a linear combination of a state 0 or 0 and 1. These states here, this alpha 0 and alpha 1, those are called amplitude probabilities, and I will come back to them afterwards. But what they mean, this is not completely correct, but they tell you how much your state is in 0 or how much your state is in 1, let's say, okay? We will see the specific definition for that in the next slide. So here you can see like just an example of a quantum state, like in which my alpha 0 is 1 over the square root of 3, 0 plus alpha 1 is square root of 2/3. Okay, just an example of a quantum state or a quantum bit. So what is the tricky part of this? So the point is that we cannot examine a qubit or a quantum state to determine its state. So I cannot read this alpha 0 on alpha 1. So what happens when I want to read out information, when I want to read out that superposition? So as I just mentioned, you cannot read that superposition state, but you get it's or a 0 or a 1. So you get binary information. And in which probability you get any of them, so the modulus of alpha 0 or alpha more squared is the probability of finding your qubit in state 0 or in state 1 when you measure it out. So in other ways, I have my qubit in a superposition state, and I measure it out, and maybe I get 0. So, and then on top of that, I collapse my quantum state to the state that I read out. So if I read 0, my qubit is collapsed to state 0. If I read out a 1, my qubit is collapsed to state 1. So I cannot read the superposition, and on top of that, I collapse my quantum state to either 0 or 1. And again, the probability of getting a 0 when I measure out the state is given a modulus of alpha 0 squared, and the probability of getting a 1 when I measure it out is given by modulus of alpha 1 squared. Yeah? So, I didn't say that at the beginning, but feel free to interrupt me anytime that you have any question, okay? So now imagine I have this quantum state that is the one that I showed before, and very important thing, by the way, that I forgot to mention is because the modulus, these are the probability of getting 0, and this is the probability of getting 1 when I measure out my state. So if I add them, it's equal to 1, right? Because they are probabilities, so they should be equal to 1. So again, if I give you this state right now, what is the probability of getting measurement result 0? Again, I repeat again. So if I give you now this quantum state, right, in which this is my alpha 0 and this is my alpha 1, and then I measure it out, what is the probability of getting measurement result 0? 1/3, yeah? And the probability of getting measurement result 1? 2/3, yeah? Everybody agrees? Yeah, so it did. So the probability of getting result 0 is 1/3, that is the modulus squared of alpha 0. This is my alpha 0, and 2/3 for getting measurement result 1. And on top of that, as I just mentioned, when I measure my qubit, I collapse the qubit to the state that I read out. But for example, here, 1/3 of the times, I will get measurement result 0, and I will collapse my qubit state to 0, and 2/3 of the times, I will get measurement result 1, and I will collapse my qubit to state 1. Okay? So this is a way, let's say, to modify your quantum state. When you measure a quantum state, you modify it because you collapse it to either 0 or 1. Now, a qubit, as I say, it can be expressed as a linear combination of state 0 and 1, like alpha 0, 0, plus alpha 1, 1, but these zeros and 1s can be also represented by vectors. That, for example, state 0 is represented by vector 1, 0, and state 1 is represented by the vector 0, 1. So just I can rewrite this expression just in this way, in which, again, my 0, it corresponds to a vector 1, 0, and my 1 to 0, 1, right? Just very simple. Now, a good way to represent a single qubit state, so these qubits that can be superposition, is by using what is called the Bloch sphere. So this expression, we can rewrite the expression of a qubit using this other expression in which we have different angles of rotation, and this is the global phase, that it doesn't have any effect in the representation of the Bloch sphere. And I can represent my qubit state as a vector pointing in any of the direction of your Bloch sphere. And just by changing these two parameters, these two angles, I change the state of my qubit. Yeah? This representation, this Bloch sphere, it's only for representing single qubit state. So one single qubit, and you cannot represent the combination of several qubits. And I will come back to the representation because it's a very intuitive way to understand what happens when you apply a gate or when you modify the state of the qubit. So now, for example, in this Bloch sphere, state 0 can be represented by an arrow pointing up or to the north pole of your sphere, and a 1 can be represented by an arrow pointing to the south pole of your state, of your Bloch sphere. Now, how can we modify the qubits or the quantum state? Right? We have qubits, that's the basic unit of information, but how can we modify the state of your qubit? So far, we have seen that by measurement, I can modify the state, right? Because I can collapse it to 0 or 1 when I measure in the computational basis in these zeros and 1s, but we can also modify the state of the qubits by applying what is called quantum gates. So in classical computing, we have classical gates, right? NANDs, ORs, ANDs, all these things. And on top of that, we can define a universal set of gates, in which with these gates, like for example, an AND or an OR, you can perform any kind of computations. These gates are logical operations. They are represented by truth tables, and they only run forward. When I say they only run forward, I mean that you cannot know the input of your gate based on the output, except for the NOT gate, okay? So you cannot know what the input was just looking at the output, except for the NOT gate. So in quantum computing, we can also define a universal set of gates. So we operate on the qubits by applying quantum gates. And again, we can define a universal set of gates that, for example, are Hadamard, T, C0, and S gate. I will come back to that. And with those gates, you can perform any kind of computation. Now, these gates are all unitary operations. They are represented by unitary matrices that you can see there, that, for example, the Hadamard is represented by this matrix, the T by this other and the S, and so on. And because of that, all quantum gates are reversible. So I can always know what the input was just looking at the output. So quantum computation is reversible. That's a property, specific property also for quantum. Now, let's have a look at these gates. So we have what they call single qubit gate, so gates that only act in one qubit. We have the most important and the most famous one are the Pauli gates. So we have first the identity. The identity is represented by this matrix, and it does nothing, let's say, to the quantum state. It maps 0 to 0 and 1 to 1. So it's just doing nothing to your quantum bit. We have the Pauli X that is represented by this matrix. This is an analog of the NOT gate in classical computer, in which it brings state 0 to 1 and 1 to 0. It's also called the bit flip gate. Now we have the Pauli set gate that again is represented by this matrix that brings a state 0, the maps state 0 to 0, so it doesn't change the state, or 1 to -1. It's also called phase gate, because what it does is just changing the phase of your quantum state. Then we have the Pauli Y that brings 0 to I1 and 1 to -I0. And one of the most important gates that is called Hadamard. The Hadamard is represented again by this matrix, and what it does, it maps state 0 to 1 over square over 2, 0 plus 1 to a superposition state, or 1 to 1 over square over 2 to 0 minus 1, that are maximum superposition state. Okay? Try to remind these transformations, because we will come back to that later. Okay? Now, as I said, a way to representing qubits is by using the Bloch sphere. So what this gate do to the qubit, it's a rotation around some of the axes around the Bloch sphere. That, for example, an S-gate, as I said before, an S-gate is called, again, Bit-flip gate, and it maps 0 to 1 and 1 to 0. So what it does, it's a rotation of the Bloch sphere around the x-axis by 180 degrees. And it brings, again, state 0 to 1 and 1 to 0. Or Hadamard, again, it brings 0 to 0 plus 1, or also called the plus state, and 1 to 0 minus 1, or also the minus state, and it's a rotation about the x and the y axis around the Bloch sphere. Yeah? So at the end, a gate, again, it's a rotation of, around one of the axes of the Bloch sphere of your qubit state. Now, that's an intuitive way to see how you can modify the state of the qubit, but how does quantum computer, how you calculate let's say, the output of applying a gate or your quantum state? How does it work? So it's all about linear algebra, okay? So what I said before is like, imagine that you have your quantum state, you apply whatever gate, a unitary gate, and you want to calculate what is the output state, or what is the result of applying that gate to your quantum state. So in order to calculate the output state, you just multiply the matrix representing this gate by the vector representing your input state. So it's all about vector matrix multiplication. Again, it's about linear algebra. Remember that I say that, for example, the 0 state is represented by the vector 1, 0, and the 1 by the vector 0, 1, and the gates are represented by unitary matrices. So at the end, again, the only thing that you have to do is to multiply vectors and matrices. Yeah? So here's where we start to work. So again, in order to calculate what is the output when I apply a gate or your quantum state, the only thing that I need to do is to multiply the matrix representing the gate by the vector representing my quantum state. So now, imagine that I have my qubit in the 0 state, and I apply an X gate. I would like that you calculate what is the output. I mean, I mentioned it before, but that you calculate what is the output of applying that gate to the 0 state. And again, for that, we have to use the matrix that represents the gate and the vector that represents the qubit, and just do this vector matrix multiplication. And if you don't remember how to do that, here is the, I know it's a long time ago for some of you, so there is a hint here. So can you please do that by hand and tell me what is the output that you get? 0, 1. 0, 1. Yes? I give a bit more time to other people. It's not a complex thing to do, but still, yeah? 0, 1. So indeed, what we just need to do is, again, to take this matrix that represents the X gate and multiply by the vector representing the 0 state, and when we get, it's a 0, 1. And this vector corresponds to what state? State 1, indeed, right? That's something that I mentioned before. So indeed, okay, doing quantum computations is pretty simple. It's just vector matrix multiplication. Okay, let's do another example. Now, I want you to calculate what is the output of applying a Hadamard to my 0 state and then to my 1 state. And indeed, and again, you have here the matrix for your Hadamard and the vector for the 0 and for the 1 state. So can you please calculate what is the output of applying a Hadamard to the 0 state? I don't see anyone writing. Okay, a couple of... Yeah, I told you before, but I want you to double check that I was right, or maybe I was wrong, and you don't know, you didn't even notice. Okay, or both. I can be both or one. Indeed. Yeah. Okay, that's a good one. So what is the result of applying a Hadamard to the 0 state? What vector did you get? Okay. So indeed, what you get is the first column of the Hadamard, so 1 over square over 2, 1, 1, that corresponds to state 1 over square over 2, 0 plus 1, right? As I mentioned before. If now I do the same, but to the 1 state, what do I get? Okay. Makes sense. I'm glad that I don't have more columns, you know? Okay, good. So indeed, if I apply the Hadamard to my 1 state, what I get is 1 over square over 2, 1 minus 1, that is 0 minus 1 state. Now, another question. If I measure those states now, what is the measurement result? What will I get? If now I measure, so I apply the Hadamard and I get 1 over square, 1, for example, 1 over square of 2, 0 plus 1, right? It's a superposition state, 0 plus 1. And then I measure that quantum state of that qubit, what result I'm going to get. What is the result of that measurement? What will I get? 0 or 1? Okay, good. So, yeah. I just wanted to double check. Indeed, so you got what I explained before, or I explained it. So indeed, if I measure any of those states, 50% of the times I will get 0, and 50% of the times I will get 1, okay? So something that I didn't mention before because of this measurement behavior, quantum computing is a non-deterministic kind of computation, okay? We always get binary results, and there is always a probability of getting either a 0 or either a 1. So it's like a non-deterministic computation. Now, let's go one step further. So far, I just use 1 qubit state. I put 1 gate, and I want you to see what is the output state. Now, I have my input state, and I apply, for example, 3 gates, and I want to calculate my output state. So in quantum computer, time goes from left to right, like in classical computing, but when you do the calculation, it goes from right to left. In other words, in order to calculate what is going to be the output state, when I apply all these 3 gates, I have to multiply all these 3 matrices, but in this order. So U3, then U2, then U1, and then multiply by the input vector. Okay? If you change the order of those matrices, of the gates, you will get something different. So it's very important to respect the order. Why? Because then the first gate, it's applied to the qubit, then the second, and then the third. Yeah? So I explained that. Now I have, again, my input state, that is 0, and this is not that easy to calculate. And now I want to see what is going to be my output state. So again, I have my 0, and then I apply a Hadamard that is represented by this matrix, then a set gate represented by this matrix, and then another Hadamard. Can you please calculate first what is going to be the matrix for these 3 gates together? So first the product of those 3 matrices, and then we will see what is the output state. So again, it's just a product of the Hadamard, the set, and the Hadamard. So you already have the resulting matrix. When you multiply all these 3 gates, what is the resulting matrix? Sorry? One's like this. Sorry? Exactly. Good. So if I multiply all these 3 matrices representing the Hadamard, the set, and the Hadamard, I get this matrix, 0, 1, 1, 0, that indeed is equivalent to an X gate, to the Pauli X. And then what it does, as I said before, what it does, this Pauli X is equivalent to an OR gate in classical, so it's called also the biflick gate, and brings maps state 0 to state 1. Yeah? Okay, let's do another exercise. Now, again, I start with my 0 state, but now I'll apply a Hadamard, an X, and a Hadamard. First, what is the matrix that you get when you multiply those 3 matrices? Did you already get the matrix? More or less. Okay. Okay, so if I multiply this Hadamard, this X and the Hadamard, what I get is this matrix 1, 0, 0, minus 1, that it corresponds to the Pauli set gate, that is a phase flip gate, and still it maps 0 to state 0, and we saw in the previous slides. Okay? So, now, so far, we have seen how to represent a single qubit state, and the superposition in this state. We have seen how to modify that state by applying either a measurement or a single qubit gate or several single qubit gates on that state. So let's go again one step further, and let's start combining qubits. So as in classical computing, you can also combine quantum states or qubits. How you write down that state? So imagine that I have my state 0, that is a superposition of alpha 0, 0 plus beta 0, 1, and my state 1, that is alpha 1, 0 plus beta 1, 1. In order to calculate the state that results from combining those 2 qubits, the only thing that I have to do is the tensor product between them, or the Kroninger product. For those who, again, don't remember what the tensor product is, it's here. So just to take the first element of the first vector and multiply with the other elements of the other vector, the second element multiplied by all the elements of the second vector, and so on. Okay? So if I combine those 2 qubits, what I get is this state in which I have 4 amplitudes, and it contains all possible states from 0, 0, 0, 1, 1, 0, and 1, 1. So here, just to let you know, I wrote down alpha 0, 0, but indeed this is the result of multiplying alpha 0 by alpha 1, and this is alpha 0, beta 1, and so on. Yeah? And again, this state can be written in a vector form, and because all these are amplitude probabilities, or the probability of getting or state 0, 0, or 0, 1, or 1, 0, and 1, 1, when I measure it out, that state, the modulus square of all these alphas should be equal to 1. Yeah? So when I put qubits together, so before I have a single qubit in a superposition state, now I have 2 qubits in a superposition state, I get a new quantum state that is composed by all possible states of combining those 2 qubits. Yeah? So this is what is called, again, superposition. So qubits can be in a superposition, and I can also superpose qubits. But there is another very important property of quantum mechanics that is called entanglement. So entanglement is two qubits in a superposition, but are correlated to each other. So in a way that these qubits that have been entangled cannot be, let's say, described in a separate way anymore. So let's see at other definitions. So entanglement, again, it's a non-local property that allows a set of qubits to be expressed with a higher correlation. And this correlation is higher than in classical systems. When you entangle particles together, what happens is when you measure one of the particles, it defines the possible outcomes of the other particle, or the possible result of the other particles. And this connection or this correlation, it doesn't depend on where the particles are, that if you entangle two particles and you put them far away, still, if I measure one of them, it will affect the result of the other one, or the state of the other one. That, for example, I give you here a very simple example of the two quantum states that have been entangled, and I get this quantum state 1 over square over 2, 0, 1, plus 1, 0. If I measure the first qubit, if I measure this one, and I get measurement result 0, I collapse to the state 0, 1, and for sure, if I measure the second qubit, I will always get 1. And again, if I measure in this state, if I measure my qubit and I get the first qubit and I get state 1, the second is collapsed to 0. So in this case, when I measure the first qubit, the second one gives me result 1, the other will give 0, and vice versa. I get the opposite. So it's a kind of correlation that is stronger or higher than the one that we can see in classical computation. So a couple of years ago, in 2015, a colleague of us, Ronald Hanson, proved that it's possible that indeed you can entangle two particles, and when you measure one, it affects the result of the other. So they ran an experiment in which, again, they entangled two particles that they were like 1.3 kilometers apart from each other, and then they observed, again, that when you measure one, it affects the state of the other. Okay? And this entanglement, they could entangle those two particles like once per hour. Every 1 hour, they will be able to entangle them. And something that I didn't mention, but it's also very important property of quantum mechanics, is that both superposition and entanglement are very fragile phenomena. So qubits have what is called a very short decoherence time. The coherence time means that they lose the superposition or the entanglement just because of the interaction with the environment. So again, they were able to generate entanglement once per hour, but it was lost in a fraction of a second, or something like that. So I would like to show you a video about this experiment that they run, and that you may understand better what entanglement means. a bit of advertisement. So again, this is an experiment that they're running in Delphi in 2015, and they were capable of generating entanglement once per hour, but this entanglement state only remained for a fraction of a second. But the good news, like a couple of weeks ago, the scientists, Ronald Hanson group, they generated what they call on-demand entanglement link. And I'm going to read to make sure that I say the right things. So now with this new method, they are capable of generating entangle 40 times per second. And they generate this entanglement between two electrons that are separated not 1.3 kilometers, but 2 meters for now. And this method is like 1,000 times faster than the previous one, the old one. So and what they demonstrated is for the first time, they can generate entanglement faster than the entanglement is lost or destroyed. So this is a big achievement. So the main application for this entanglement is for quantum communication and quantum internet or networking. That is the goal of this, in this case of Ronald Hanson group and Stephanie's group, is to build the first quantum internet or the first quantum network in the Netherlands, between different cities in the Netherlands. Anyway, so I hope that you understood what is entanglement more or less, and that it's possible and it exists and it's there. So there is a mathematical way to prove that two states or more states are entangled. So it says that two qubits are entangled if their joint states cannot be possibly separated into products of individual states. That, for example, if I can write down my quantum state, in that way, so that means that it's not entangled, it's just a superposition of states. But if I cannot do it like that and I have to do it in this other way, it means that your quantum state is entangled. So here you can see just an example of this 1 over square over 2, 1, 0, 0 plus 1, 1, that it can be separated into two individual states, and the product of two individual states, like one tensor product with 0 plus 1, but in the other case, it's not possible. So there is a mathematical way to prove or to demonstrate if two qubits or more qubits are entangled or not, or it's just a superposition. So let's continue with the quantum circuit. So far, I have been talking about single qubit circuits or single qubit states and single qubit gates. Let's talk about circuits with more than one qubit. For example, here I have a 2 qubit state, 0, 0. As I mentioned before, I can write down the state of this qubit just by doing the tensor product of this 0 and 0. That it can also be write down like that or like this. It just this 0 corresponds to the top qubit, to the blue one, and this other 0 to the red line. And indeed, if you do the tensor product of these two vectors, so it's just vector 1, 0, 1, 0, you get a vector that is 1, 0, 0, 0. In the same way, if now, for example, my bottom qubit is in state 1, this corresponds to state 0, 1, and the state 0, 1 is represented by the vector 0, 1, 0, 0. So if I do the same for 1, 0, it's this vector, and so on, okay? So when I combine qubits, the only thing that I have to do is the tensor product of the vectors representing that quantum state of that qubit. Now, imagine that again, I have these two qubits in state 0 that is represented by these vectors, and then I apply a gate on the first qubit and another single qubit gate in the second one. So how do I calculate the result? So what I need to do, again, is to do the tensor product of the first gate and the second gate, and then multiply by the input state. So again, in the qubits, in order to write down this state, I just do the tensor product between the two qubits. So here, I do the tensor product between the top and the bottom gate. So now, let's do another example. So imagine that I have my 2-qubit system in which both qubits are in state 0, and then I apply a hallmark on the first qubit, an identity or nothing on the second qubit. So again, in order to calculate the output state, the first thing that I need to do is to do the tensor product between the hallmark and the identity state. And here, again, you have the formula how to calculate that tensor product. Can you please write down the matrix of the result of multiplying this, or doing the tensor product of these two matrices? What you get? What is the matrix that you get? So here, in order to do this tensor product, I have to take the first element and multiply by all the matrices. The second element, multiply by all the matrices. Yep. Did you get the matrix? Sorry? This is it's an identity matrix? In the second one, it's an identity, the first is a hallmark. Yeah, but I would like you to see what is the final matrix that you get. So what is the result of doing this tensor product? Or just tell me what is the dimension of the matrix that you get. Just tell me. Okay, good. So if I do this tensor product, I get this matrix that is 4 by 4. So before, when I was applying a single qubit gate, this single qubit gate, the matrix representing the single qubit gate is 2 by 2. And now that I have 2 qubits, it's 4 by 4. That means that the dimension of the matrix is 2 to the n, being n the number of qubits. So if I have 1 qubit, it's 2 by 2. If I have 2 qubits, it's 4 by 4, and so on. You have 3 qubits, 8 by 8, and so on. And now that I have that matrix, what I need to do to calculate the output state is just to multiply that matrix by the input state, right? Yes? Yeah? So if I do that, I will not ask you to do that, so I just took the result of doing the tensor product of the hallmark and the identity, that is this matrix, and I multiply by the input state, that is 0, 0, and corresponds to the vector 1, 0, 0, 0. Okay? If I do that, what I get is 1 over square over 2, 1, 0, 1, 0, that can be like decomposed in these two other vectors. What state is that one? If I wrote down in, let's say, not in a vector way, but in like more quantum state way, let's say. 0, 0, plus 0, 0, plus 1, 0. Yeah? So this represents the state 1 over square over 2, 0, 0, this vector, plus 1, 0. Good. But now the question is, when I have this kind of circuit that are pretty small, do I want to do all this vector matrix multiplication and spend my time doing all these tedious things? So there is a faster way to do these calculations and to calculate the output when the circuit is simple. So there is a faster way to do that. Let's see how to do that. So here, as I said before, here the state is 0, 0, right? Being this first qubit, the blue one, and this second qubit, the red one, right? I can write like that. Then I see, I apply a hallmark to the first qubit and nothing to the second qubit, right? And I know that my hallmark brings the 0 to the 1 over square over 2, 0 plus 1. The identity does nothing to your qubit. Then I can do it very simple. So I have my 0 state, I apply a hallmark, so now my 0 state goes to 1 over square over 2, 0 plus 1, and the second qubit that I apply identity stays the same, right? So I can write it down like that. And then I just need to combine, to multiply those two states, and I get 1 over square over 2, 0, 0, plus 1, 0. Yeah? Is that clear? Any questions so far? Yes, no? Feedback, please. Yeah. If you measure the first or the second? If you measure the second one, what do you think? If you measure the second one?
The second one, it's like the whole equation, right? So you measure
No, so this is the first qubit, so this is the first qubit, and this is the second qubit. You see, let's just start here again. So I write down here 0, 0. This 0 corresponds to the blue line, and this 0 to the red line. Yeah? Then apply a hallmark on the first qubit. So this one goes to 1 over square over 2, 0 plus 1. And the second stays the same. And then if I rewrite this expression is 1 over square root of 2, okay, I put it out, and then it's 0, 0, plus 1, 0.
Almost, yeah.
Almost, yeah. So this corresponds to the state of the first qubit, this 0 and 1, and this 0 is my second qubit. No, do you see that? So again, this is my first qubit, and this is my second qubit. So the first component, let's say, of your state, and the second component. So that corresponds to your first qubit, and this is the second qubit. Yeah? Almost there? Okay, no, we can look at that later. Okay. Okay. Good. So now, so far I have been talking about single qubit gates, but we also have two-qubit gate, or multi-qubit gate. So one of the most popular two-qubit gates is called the CNOT. It acts on 2 qubits, and it's represented by this dot and this open circle here. So what does it do? So the CNOT gate, what it does is like, if this is called the control qubit, and this is my target qubit. So if my control qubit is 0, so imagine that my control qubit, again, is 0, nothing happens to the target qubit, so it remains in the same state. But if now my control qubit is 1, it flips the target qubit, so the second qubit goes to 1, okay? This CNOT can be expressed like a truth table of an XOR gate, and is represented by this matrix. Again, the CNOT gate operates in 2 qubits, the control and the target. If the control is 0, the target qubit remains the same. If my control is 1, it flips the target qubit, going from 0 to 1 or from 1 to 0. Yeah? There are other multi-qubit gates like the swap gate. The swap gate, what it does, it exchanges the state of my qubits. So I have A, B, and it goes from B, A. So exchange, again, the state of the qubits, or swaps the state of the qubits, or another 3-qubit gate that is called the Toffoli gate, in which I have 2 controls and 1 target, and what it does is to change or to be flipped the target qubit if both controls are 1. It's similar to the CNOT, but now with 2 control qubits. So if both are 1, my target qubit is changed from 0 to 1 or to 1 to 0. There is a bit flip there. Now, let's now play with this gate. So again, imagine that I have, sorry.
What is the point of having a swap gate?
What is, sorry?
Why do we need a swap gate? Do we ever use a swap gate?
Why do we need a swap gate? That, for instance, I'm going to give you a very simple example. So in quantum processors, we have limited connectivity between the qubits. That, for example, you only have a 2D array in which only nearest neighbors can interact or can perform a 2-qubit gate. So if I want to perform a 2-qubit gate between 2 qubits or 2 quantum states, let's say, that are far away, or not far away, but are not connected or cannot interact, you need to move your states in your lattice. So for that, for example, you use swap gates. But they are also used for computation for other purposes. Okay? But it's to exchange, to move information. You can use for moving quantum information in your quantum chip or in your quantum processor. Yeah? So let's start playing now with these 2-qubit gates too, and imagine again that you have your quantum circuit with 2 qubits, and here, as I said before, I can write down this state like 0, this is the blue one, and 0, this is the red one, 0, 0. Okay, this is the state here. So what is the state after applying the hallmark to the first qubit? I know I showed it before, but now I want you to see if you, and don't do matrix multiplication, vector matrix multiplication, eh? Just apply the Hadamard to the first qubit. Again, the first qubit is the 0 state, and Hadamard, what it does is map the 0 state to the 1 over square over 2, 0 plus 1. So what is the output state here in 2? What is my state in 2? Sorry? Okay, we did it before, right? So again, I apply a Hadamard to the first qubit. So I apply a Hadamard here to the first qubit. The second stays the same. And then I rewrite that expression, and I get 0, 0 plus 1, 0. And now I apply a CNOT between, again, the first and the second qubit, in which the top one is the control. What is the output after applying what is the quantum state after applying the C node? It's a C node. Again, a C node flips the state of the target qubit if the control is 1. 0, 0 plus 1, 1. 1 over square root of 2. 0, 0 plus 1, 1. Yes? No? I don't know. Both of them. Indeed. So what it does, good, thank you. What it does is, again, flips the target qubit if the control is 1. Here, this is 0. That is the control. The target stays the same. The second stays the same. But here, because the control is 1, the second goes to 1. So it's 0, 0 plus 1, 1. Yeah? Is this clear for everybody, or more or less? OK, if you don't say anything, I'm assuming that it's clear. OK. If not, I will try to rephrase that later. Anyway, so by using this circuit, this Hadamard, and this CNOT gate, what I created is an entangled state that is one of these, that is called Bell state. So I just created this 0, 0 plus, 0, 0 plus, yeah, 0, 0 plus 1, 1, but I can create other three entangled state, Bell state, if I start from different values, if I start from 0, 1, or 1, 0, or 1, 1. So these Bell states, we use them a lot in quantum computing, especially in quantum communication, and in quantum teleportation. So I guess that you may have heard about quantum teleportation, not only in Star Trek. Now it's possible, at some point it will be possible. How does it work? So quantum teleportation works as follows. So the first step in quantum teleportation is to create one of these entangled states, one of these Bell pairs. So you take two particles, you entangle them, for example, in the way that we have shown in the video, or better way, you entangle them, and then you give one to the sender, that in this case is Alice, who wants to send her state to Bob, okay? So again, the point of quantum teleportation is Alice wants to send her quantum bit or her quantum information to Bob. And for that, the first thing that they do is to create a entangled state, a Bell pair, and Alice takes one of the particles, and Bob takes the other particle. And they are far away. They can be wherever they are. So then Alice, with the half of the Bell pair, what she does is, together with the state that she wants to send, she does what is called the Bell pair measurement. That is a C node, a Hadamard, and then she measures both bits. So the quantum bit, the quantum state that she wants to send, and half of the entangled state. So at the end, if she measures these two qubits, what she gets is 2 bits, right? Those 2 bits can be or 0, 0, or 0, 1, or 1, 0, or 1, 1. Because again, when you measure qubits, what you get is binary information. You only get zeros and 1. And she sends those 2 bits, this classical information using a classical channel to Bob. And then Bob, based on that, he should have received or the state, exactly the state that she wanted to send, or he will have to make some corrections depending on those two binary results. Okay? So that's the basic idea of teleportation. So again, what we are giving, what Alice is sending to Bob is not the qubit itself, it's because that quantum state is teleported, but it's just sending 2 bits using a classical channel. Yeah? So we will see that how it works. So this is another way to write it down. I will put it in that way, because we will use it afterwards in the QX simulator, but are exactly the same gates that I showed before. And now I would like you to do some exercises, some very simple exercises, and then we will continue with example of teleportation. And we will demonstrate that indeed teleportation, this circuit that I've shown, it works, and how it works. Okay, but before, I would like you to do the first exercise, in which you have 2 qubits in a state 0, and then you apply an X on the first qubit, and then a C node between the first and the second qubit. now. What is the result of exercise 2? 0, 1? Yeah, 0, 1? Yes? Okay, 0, 1. So what is the output of exercise 3? 0, 1? Yeah? And then, and what was the output of exercise 2? 0, 1. The same, right? And we started with the same state, 0, 0. So what does it mean then? So in exercise 2, we apply an X, so just means that we put the first qubit on the one state, and then we perform 3 CNOT gates, right? And in the second one, in the third one, in exercise 3, I start also with state 0, 0. I just flip the first one, so I put it in the one state, and then I do a swap. And I get the same result, right? You got the same result in both. So what does it mean? If you look at the circuit. Sorry? Yeah. Yeah, exactly. So what it means is a swap gate is equivalent to these 3 CNOT gates. Well, swap gate can be implemented by doing these 3 CNOT gates in that way. That's what it means. And now, what is the output of exercise 4? 1, 1, 1? Yeah, everybody agrees? Okay. Okay, good, very good. So in the second part, so in the next lecture, we will do the same exercises by using the QX simulator. So now you understand how it works, so you understand how apply gates on your qubits. Now let's have a look to quantum teleportation. As I said before, in order to teleport a quantum state, so Alice wants to teleport to send her quantum state to Bob, we run the following circuit, in which first we create a bell pair, or we create an entangled state, and we send half or give one particle to Alice, the other particle to Bob, and then what Alice does is she measures the 2 qubits that she has, and then she sends 2 classical bits using a classical channel to Bob, and depending on that, Bob has received or the correct state, we still have to make some modifications. So just a note here, so this case, these are controlled binary gates, that depends on the measurement result. If the measurement result of this one is 1, it performs a set gate on this qubit, and if it's 0, it does nothing. And the same here, if the measurement result is 1, it performs a bit flip on the third qubit, or if it's 0, it does nothing, okay? So it's just binary control gates. So if the measurement results are 1, they do or a bit flip or a phase flip. So here I just wrote down these gates that I apply to the qubit. So the first is an X on qubit 0, then a Hadamard on qubit 1, a C0 between Q1 and Q2, in which Q1 is the control qubit and Q2 is the target qubit, and so on. I just wrote down the operations in that way, right? This is similar to the language or the programming language that is called Quasum or Quasum assembly language that we will use for writing circuits in the QX simulator. So, but let's see how this circuit works. So first, I'm going to write down the state here before doing anything as Q0, Q1, Q2, Q0, Q1, Q2, and I'm going to say that all these 3 qubits are in state 0. So I have the state 0, 0, 0, 0, 0, 0. Okay? Now, the first thing that I do is to apply an X on my qubit 0. So on the qubit that I want to send, it means that it goes to state 1, right? In the qubit 0, I apply an X, and it goes to 1. That means that 1 is the state that Alice wants to send to both, or wants to teleport. Yeah? Again, this is the state that I want to teleport, and I apply an X gate. I put it in that way because in the QX simulator, qubits are initialized by default to 0, and if you want to initialize them to 1, you have to do an X gate. That's why I put it in that way. Eh? But I could also write down here from the beginning that my qubit 0 is in state 1. Okay, so 1 is the state that Alice wants to teleport. And then I apply a halo mark on my qubit 1, on this one. So what is, after applying the halo mark, what is the state that I have? So I have a 1, 0, 0, and then I apply a Hadamard to the qubit in the middle. Just give you a couple of minutes. So if I apply a hallmark on the qubit 1 in the middle, so it means that, and it's in state 0, it goes to 0 plus 1, right? With the 1 over the square over 2. So indeed, here I apply a hallmark on Q1, the qubit in the middle. So this is 1, the 0 wants to 1 over the square over 2, 0 plus 1, and the last one stays the same, right? And I can rewrite this state as 1, 0, 0, plus 1, 1, 0. Yeah? Everybody with me? Yes? Good. Now, very simple, I do a C node between qubit 1 and qubit 2. So I do a C node between this and this, right? So 1 and 2, and this is 1 and 2. So what is the result after applying this C node on 1 and 2? 1, 0, 0, 1, 1, 1. It's a C node between 1 and 2. So between the second, between this and this, these two. So this is the control. Again, this is the control, this is the target. So because this is 0, this stays the same. Because this is 1, it flips the other one, right? 1, 0, 0, 1, 1, 1. Now I do another C node, but now between 0 and 1. So between this and this. So what is the state there afterwards? One, 0, 1 plus between 0 and 1. I made a mistake, no 1 and 2. 0 and 1 again. 1, because this is 1, it flips that 1, so 1, 1, 0, plus 1, 0, it flips that 1, 1, 0, 1. Yeah? Okay. And finally, I apply a halo mark on Q0, so that I do it myself. So what I do is now this 1 goes to 0 minus 1, and this 1 goes to 0 minus 1, and what I get is this is the full state that I get, right? After running the circuit. So again, here at this point, before measuring out, this is the state that I get, right? And then what Alice does is that she measures qubit 0 and qubit 1. So she measures the first 2 qubits. So I can get, as I said before, or 0, 1, the measurement result can be or 0, 0, or 0, 1, or 1, 1, or 1, 0. Those are the 4 possible measurement results when I measure qubit 0 and qubit 1. Yes? So again, I measure qubit 0 and qubit 1, and then when I measure them out, I can get or 0, 0, or 0, 1, or 1, 0, or 1, 1. And those are the bits that I send to Bob. Let's see. Imagine that when I measure, I get 0, 0. When I measure, I get 0, 0, it's because I get this result. That means that my third qubit is in state 1, right? And this third qubit is the one that Bob will receive. So indeed, Bob has received the one that Alice wanted to send, and there is no correction. That's exactly the state that Alice wanted to send. Right? If he wanted, I say I initialize my qubit to 1, I wanted to send a 1, and if I measure 0, 0, then Bob has the 1. Now imagine that I measure a 0, 1. So if I measure 0, 1, that is here, what Bob gets, it's a 0. But that's not the state that that Alice sent, right? She sent a 1, so and both now has a 0. But because I measure 0, 1, it means that because this measurement result is 1, it will be flipped, this third qubit, or the qubit that both will receive. So that means that I be flip qubit 2, and then I receive a 1 again. So I perform the correction according to the measurement result, and then I get 1 again. Now, if I measure 1, 0, so if I measure 1, 0, Bob received a -1. But that's not the one I wanted to receive. But because the measurement result of this one is 1, it performs a phase flip, and then I get, if I make a phase flip to -1, I get 1. So again, I get the 1 that Alice wanted to send. And if I measure 1, 1, what Bob receives is -1, but because the measurement result, those two are 1, are 2. I perform a big flip and a phase flip. And at the end, I get, again, a 1. So we have shown how teleportation works mathematically. So I just use a very simple example in which Alice wanted to send a 1, but now if you send the 1 for 0 or for any state in superposition, Bob here, you should always receive the state that Alice wanted to send. Okay? There are things I couldn't cover anything here. I just wanted to show what quantum computing, as I say in my title, it's about. That again, it's about linear algebra and vector matrix multiplication. And now you know how to perform very simple calculations in quantum computing. What I mentioned before is like qubits, again, are very fragile units, and they easily use the superposition or the entanglement just because with interaction with the environment. And if you want to perform any kind of reliable computation using quantum computing, you will have to use quantum error correction. So quantum error correction, it's a very, tricky and very difficult topic that we also work on. I will not explain that today. Koen will explain a bit about quantum error correction tomorrow. Indeed, it's something that to keep in mind. And the other important thing, again, is that quantum computing is a non-deterministic computing because of this measurement behavior. So I think I'm just right on time, right? Here, okay, I have some useful references and some references also to lectures, a MOOC by Marcilianis. We are also offering now a QTech. In QTech, we also have what is called QTech Academy, in which we are just making some MOOCs that are online in edX. From September on now, there are some MOOCs about the basics of quantum computing. And in September, we will have a new MOOC on how to build a quantum computer. So it's a very hot topic too. And yeah, that's it. Thank you.
Well, thank you very much. That was really good. Now, we do have some time for very quick questions. I think since we're going to have a second lecture, we can, if some of the questions can't be answered right now, we can leave them for later. But for now, we do have time for 1 or 2 questions. Okay.
There was,
yeah. Go ahead.
I don't know, maybe I'll talk with you outside of here, but I still don't get the fuzz about entanglement. I don't,
okay.
I just don't
It's very
get.
difficult to explain, yeah.
It's because I was told, it's probably since when I was 13 or 15, that I'm trying to, if I look at these as probability distributions, and we admit that everything we know and everything God or the particle itself knows about its state is a probability distribution, it doesn't seem that strange as everybody, it doesn't seem to me that strange as everybody is assuming it should be. It's I don't know.
Okay, but the thing about the entanglement is it's just, first is this non-locality property, in which when you entangle two particles, they are kind of linked to each other, and they are able to let's say, to have an effect on the other. If I measure this, what I say, if I measure this one, I already know what is going to be the outcome on the other one. I will collapse the other one. How exactly entanglement works, I cannot answer that question. I don't know if there is any physicist that is able to really go into the detail and explain that thing, because yeah, it's a very strange phenomena. But the only thing that, I mean, the basic idea is what I explained. I mean, they are correlated in a way that you cannot correlate classical information, and in a way that until you don't measure out one of them, you don't know what is going to be the result of the other. So you cannot know beforehand what is going to be the result of that measurement or that correlation.
But that applies to any quantum state.
Sorry?
That applies to any quantum state. That's not specific to correlation. We don't know.
No. That's what is called in the quantum state, indeed. But you can correlate because you can also correlate things classically, right? But you know, in that case, you know beforehand what is going to happen. Just like I will show you. If not, I will show you in the slides. I also put a link to a video on explaining entanglement by a professor from Australia, Andreas. How it's called? I don't remember his name now. Anyway, that it makes a comparison between, let's say, correlation in classical information and the correlation that you see when you entangle particles. Mm-hmm. Maybe you will see that. I mean, you will understand that better.
Okay. So, question there. Anyone else? Okay.
Is this working?
No. Yes, it's working.
It's working, okay. So I'm trying to understand this quantum teleportation phenomena because I haven't really seen it working before. So effectively what you are doing, you are deleting information from qubit 0 and copying it to qubit 2 that was sent directly to Bob, right?
You're talking now about teleportation, right?
Yeah.
Okay.
So as I was saying, I think we had a very different idea of what quantum teleportation would be. So we are trying to understand what that process means.
Okay.
And I'm asking you if, in a nutshell, what's going on is you are deleting information from qubit 0 because of the measurement, and then you are passing it on to qubit 2 without fabricating a new qubit, so to speak. So you are passing on information.
Exactly. The only thing that I transmit is, the point is I'm not transmitting quantum information. I'm just sending classical information. And based on that classical information, Bob is capable of getting the quantum state that Alice wanted to send. So that's the point. So you don't need you need a quantum channel to generate entanglement and to send the particle, because you generate entanglement wherever it is. 2 particles, then you give 1 particle to Alice and 1 particle to Bob. For that, you need a quantum channel, okay, for sending those 2 particles. But then the only thing that she is sending to Bob, it's only classical 2 bits, 2 classical bits, and for that you need classical channel, like we do it nowadays.
So it would be an interesting application for transmitting quantum information in a robust manner, right?
For quantum communication, yeah.
Yeah, okay, thank you.
Yeah, that's the basis of any quantum communication or internet, so.
Perhaps one last question and we go for... No, we'll have time.
Hi. I was a bit curious about your comment that quantum computing is non-deterministic. Mm-hmm. To explain my background, I work in heuristics for combinatorial optimization problems, and I am under the impression that in a few years, quantum computers will put me out of business. My idea was that, for instance, if you have one problem that is a base, for instance, yes, no, you can have 0 and 1s. In computers right now, you can evaluate one solution at a time. With a quantum computer, I was under the impression that with superposition, you could evaluate all the state space basically in one go. But if you say that it's non-deterministic, can you really solve a combinatorial optimization problem by analyzing the state space in one go, or is it more complicated than that?
Okay, I didn't, that's something that Kung will explain tomorrow better, but I can. So the idea is like, again, by combining these qubits, it's what you say, if you combine 2 qubits, you have a state that has 2 to the 2, so 4 possible amplitudes, right? So you combine 3 qubits, so you have a state with 8 amplitudes or 8 states. So what is giving you is like when you process or when you operate on these 2 to the n states, you operate in all of them at the same time. So that is giving you, so quantum is giving you maximum parallelism for free, Okay, let's put it in that way. So you can operate on those states at the same time. That's why quantum computing can be faster than a classical computer. Then, when you measure it out, you just measure one of the answers. Or I measure, if I have 4 states, let's say, in superposition, I measure 0, 0, or 0, 1, or 1, 1, or 1, 0. So what quantum algorithms work, let's say, is like you modify, you play some tricks in order to amplify the amplitude that contains the correct answer. That, for example, imagine you start with an equal superposition of your state, 0, 0, 0, 1, 1, 0, and 1, 1, with equal superposition, so you have 20% chance of getting any of those answers. But you know that the correct answer is 1, 1. So in your quantum algorithm, you modify those amplitudes, and the amplitude of the 1, 1 state will be higher than the other amplitudes. That means that maybe you have an 80% of probabilities of getting result 1, 1. But still, you have 20% of getting any other grown result. That means that in a quantum algorithm, in order to get the correct answer, you will have to run your quantum algorithm several times. Now, what several times means, I don't know. It's going to be 10 times, it's going to be 10,000 times, 1 million times, that we don't know. So that's what I mean by non-deterministic computing. So again, there are tricks for getting the right result. You only get one result, but maybe it's not the good one. So you have to run it several times to get your answer.
Okay. Thank you.
It's something similar like you do statistical tests, where you have a level of confidence, and so you keep repeating the calculations till you reach a level of confidence that you're happy with, and then that's your acceptable answer.
Yeah.
Okay, well, thank you very much. So we'll have refreshments or not. It may be a superposition state outside, so let's go for a break. Yeah, thank you.